Welcome back. So we will now talk about modular arithmetic. If a and b are integers and m is a positive integer, then a is congruent to b modulo m if m divides a minus b. If m divides the difference of a and b, we say a and b are congruent modulo m. We use the notation a 3 lines b mod m to indicate that a is congruent to b modulo m. So this symbol, this expression is read a is congruent to b modulo m. If I draw a line across like this, then that means a is not congruent. Okay, we say that a congruent to b modulo m is a congruence and that m is its modulus. Plural of modulus is moduli. We say we write a not congruent to b is missing here, b modulo m if a and b are not congruent modulo m. Note, congruent modulo m is different from the function a mod m. You see, a mod m represents the remainder when a is divided by m. Whereas this actually says that a minus b is divisible by m. Okay. Now let us understand modular numbers using an example, a concrete example. When m is 12, look at 15 and 3. 15 minus 3 is 12 times 1, right? Because 15 minus 3 is 12. In other words, 15 minus 3, the difference is divisible by 12. So 15 is congruent to 3 modulo 12. 18 and 6. 18 minus 6 is also divisible by 12. So you say 18 is congruent to 6 modulo 12. Look at 23 and 47. 23 minus 47 is negative 24. Negative 24 is divisible by 12. So 23 and 47 are congruent to 11 modulo 12. Right. So 23 minus 47 is divisible by 12. So you can say 23 congruent to 47 modulo 12. This is how you would write 27. Notice 23 congruent to 11 modulo 12 as well. All right. So one way of thinking about this is you understand the clock, 12 o'clock. What is 15 o'clock? 15 o'clock is actually 3 o'clock. What is 18 hours? It's 6 o'clock. 23 hours, that is 11 o'clock. In the same way, 47 hours is also 11 o'clock. I use the example of 12 first because you know the meaning of a 12-hour clock. Instead of a 12-hour clock, suppose you are looking at a 17-hour clock. So 17 is the top number. 1, 2, 3, you keep going, right? Somewhere here is 16. After 16 is 17. After 17 is 18. 18 o'clock in a 17-hour clock is back to 1. 19 is back to 2. And so on. I hope it's clear. So 18 minus 1 is divisible by 17. 18 and 35. The difference is also divisible by 17. So 1, 18, 35, they all land in the same 1 o'clock. 2, 19, 36, 53, they will all land in 2 o'clock. Okay, so that's what modulo congruence modulo m represents. Let's look at a theorem. Let a and b be integers and m be a positive integer. Then a congruent to b modulo m if and only if a mod m equals b mod m. What does that mean? If and only if. So let's go through this carefully. A proof of theorem 3. Okay. So if and only if. That means you want to start with one side as a hypothesis, prove the other, and conversely. So let's assume, suppose that a congruent to b modulo m. We want to show that a mod m equals b mod m. What does this mean? This means the remainder when a is divided by m is equal to the remainder when b is divided by m. We know that a is congruent to b modulo m. All right. Now, so let's see. Since a is congruent to b modulo m, we have a minus b is divisible by m. What does that mean? There is a number n such that m times n is a minus b. Therefore, a itself is mn plus b. Alright, so a is mn plus b. Now let's look at, I want to say that a mod m equals b mod m. In other words, we want to show that when a is divided by m, the remainder you get is equal to the remainder you get when b is divided by m. Okay. Let us consider the division of b by m. Suppose q is the quotient and r is the remainder, then b is divided by m. What does that mean? That means b equals qm plus r. Okay, and most importantly, r is between 0 and the divisor m. Okay, so at this point, you recall here a equals mn plus b. Therefore, a itself is mn plus b. B in turn is qm plus r. So that is same as, look at that, m common n plus q plus r, where r is between 0 and m. You see? Okay. So in other words, remember one very important thing, the division algorithm states is that you should have unique integers q and r, such that r is between 0 and the divisor and your number is divisor times quotient. So this quotient and this remainder has to be unique. We found a quotient. In other words, r is indeed the remainder when a is divided by m. You notice, which is what we want to show. right? We want to show that the remainder when A is divided by M is equal to the remainder when B is divided by M. And we just said R is the remainder when B is divided by M, and R is also the remainder when A is divided by M. That is, we have shown that A mod M equals B mod M. So one way implication we managed. We assumed A is congruent to B mod M, and we proved that A mod M equals B mod M. Now we prove the converse. Suppose A mod M is equal to B mod M. That is, the remainder when A is divided by M is equal to the remainder when B is divided by M. Now we want to consider, okay, so what does that mean? That is, let us call this remainder R. All right, that is, there are integers q sub 1 and q sub 2. The quotients given by the division algorithm. When A is divided by M, so suppose first quotient times M plus remainder, and B is the second quotient M plus remainder. All right, now consider A minus B. What is A minus B? It is QM plus R, that's A, minus Q2M plus R. All right. So notice, what does this say? This subtraction is for the entirety of B. That's why I needed parentheses. So this is Q1M minus Q2M plus R minus R plus 0, which is equal Q1 minus Q2 times M. So you see, A minus B is divisible by M. That's it. We have proved the converse. Okay, this is how you prove any result, any if and only if result. Okay, one way, that's assume this, prove this, conversely assume this and prove this. All right, we'll stop this section here. We'll continue theorem 4 in our next video.